quietly. Oh, well, I'm very pleased to welcome Craig Storey to our meeting this evening. I love the slide there. There's two things on that slide. Do I?
Hello. There's two things on this slide I like, omphacite and garnet. That summarizes my entire life for the last 40 years. The glaucophade, the blue stuff, I'm aspiring to know more about. So we look forward to hearing from Craig. So I'm going to try and do this off the top of my head, a biog.
Nice.
But one thing I can't remember is where you did your first degree.
Oxford Brookes.
Oh, well, there we go. I should have remembered that.
Mm.
And then you did your PhD at Leicester University.
Correct.
And then went off to do some postdoctoral work at Bristol and...
Yeah, the Open University. And I was at the Natural History Museum.
All over the place. And currently at the University of Portsmouth. He's got some done a lot of very interesting work since Bristol on the onset of modern style plate tectonics, which we hope to hear about this evening. So over to you.
Thank you. Thank you. Good evening, everyone, and thank you very much for inviting me. I've had the pleasure of hospitality already and a nice hotel. So yeah, really great pleasure to be here. What Simon said there is also true of me. So I started out doing my PhD on eclogites. So omphacite and garnet was my kind of first love as a mineral and as a rock type. And over the years, I started to do more work on geochronology to try and understand the timing of this high pressure metamorphism. And from that, I've kind of developed over the last sort of 15 years into trying to answer this question here, which is something which I could spend my whole life and many other lives addressing. But the good thing now is I hope I've got some sort of story to tell you about this question that you may or may not believe. That's up to you. It's nice that after a prolonged period of time that I'm actually kind of getting to posing some interesting kind of opinions, I hope, for you. So next slide. So this is what we're going to talk about today. First of all, I need to tell you what we think is the modern style of plate tectonics and how we might distinguish that from other styles of plate tectonics which might have existed in the past. So that's the important thing, first of all. And then we're going to look at what are some of the hallmarks of plate tectonics, which rock types, which rock associations, which processes occur, which are the hallmarks of modern style plate tectonics. And then once we've done that, then we can discuss how we can look for those in the geological record and think about how we can date those so we can get the secular evolution of when this modern style of plate tectonics first came to be. So that's what I will attempt to do. Okay, next slide. Right, so here is a nifty little definition of what we might consider to be plate tectonics. So this is from Peter Kaywood a few years ago, and his definition there is a mosaic of rigid, mobile lithospheric segments that plunge against each other, leading to production and differentiation of the crust. And obviously the point is there, as the title of the map suggests, is it's perennials, it's ongoing, you can't stop it. Oops. At some point we might stop it, but the conception of plate tectonics is an ongoing process. So we need to bear that in mind when we go back in time to see how we can test that this actually is actually realized for something that we'd want to call plate tectonics. And the reason why I'm dwelling on this is there is actually a lot of confusion in the literature. People use the terms plate tectonics, subduction interchangeably, but they don't often define what they mean by that. And we need to do that if we're going to actually address the question I'm trying to address. Okay, next slide. So I'm sure you're aware of these types of diagrams, these kind of simple block diagrams which remind us of the major features of the plate tectonic system. So we're forming new crusts at mid-ocean ridges, and as that spreads, it cools, and then comes a subduction zone. And above the subduction zone, we have volcanoes at continental margins, and we form new continental crust potentially. Okay, we can also form new continental crust eventually in ocean islands, which might then become later accreted onto the edges of continents. So there's a number of things we're doing here. We're building new crust, we've got ongoing subduction, and we can also recycle older crust as well. Okay, so that's the take-homes from this particular diagram. Next slide. So these are, I've boiled this down because the list would be much larger than this actually, but this is what I'm going to deal with in this particular lecture. The hallmarks, what I'm going to talk about today of modern style plate tectonics. So the first thing is continental crust, and that doesn't necessarily mean that the continental crust needs to have modern style plate tectonics, right? But it means that this is one of our major repositories for learning about the history of plate tectonics. Crustal recycling is something that needs to happen if we have plate tectonics. We need to have, if we're moving mobile rigid plates around in continents, we need to have periods of supercontinent formation. That's something we need to achieve. And going back to mine and Simon's first love, we need high pressure metamorphism, and specifically high pressure, low temperature metamorphism that we only see in modern style subduction zones at present day. And this is our only planet where we form these types of rock. And the other thing is paired metamorphic belts, which I'll talk about in a few slides' time. So these are some of the things that we'll first of all just go through and just define, and then we'll look at some of the records, going back in the rock record, before we can start to kind of synthesize and see if I can answer the question I posed to you. Next slide. Okay, so just step back a moment or two. The reason why continental crust is so important is because it's long-lived. So the oldest bits of continental crust are around 4 billion years. And if we take detrital zircons as records of continental crust, and it might even be as old as 4.4 billion years. However, we know that oceanic crust is only as old as around 180 million years. So in the rock record, if we're going to try and go back and learn more about ancient tectonic processes, we really need to be interrogating the continental crustal record. So of course we might have bits of old oceanic crust preserved as ophiolites, but the record is quite patchy. I did have some slides I was going to put in here, but actually the talk was getting too long, and the record from bits of ophiolite is not actually that good. So that's another thing we need to take in mind. Okay. Hey, good. Thank you. Yeah, next one, please. So the continental crust. Let's just take a little kind of look at what we mean by the continental crust. So we're dealing with something which is around 30 to 40 kilometers thick, but is actually only a very small volume of the Earth. So it's at less than 1%. It's highly differentiated. So that means that things that came from the mantle have been highly differentiated. And so we end up with a cross section through typical crust with much more buoyant felsic lithologies, but still with a more mafic base at the bottom. And it's a major store for lithophile elements, radioactive elements. So it's relatively warm and mobile as a result. Okay, so next slide. And the important thing, if we take a whole kind of crustal geochemical signature from the entire continental crust, is that we have here bulk continental crust in red. We can see this trace element spider diagram has a very similar signature to island arc basalts, okay, as you can see here, but very different signature to rocks which are formed in plumes or in ridges. So for this reason, this paper from 1995 now, Roberta Rubnik suggested that around 80% of the continental crust was formed by subduction. So in other words, from this, on the basis of this bulk geochemistry, one interpretation is that we need subduction, at least, to form the continental crust, right? So this is an important starting point for us trying to form this argument. Next slide. And the other thing that's important to remember, to know about, is that actually when we form continental crust, and that means we extract stuff from the mantle, we melt the mantle, we extract it to form the crust. Now that actually happens in two stages. So primitive arc lavas are basaltic in composition, but the bulk of the continental crust is actually andesitic. So we have a differentiation process which forms a more differentiated continental crust. And as a result of that, we must be losing some of the more ultramafic material as cumulates back into the mantle. But the point really is that if we're actually forming new crust, it must be a new addition from the mantle, not reworking of stuff that's already there. So if we're growing the crust, we need to be melting the mantle and adding new material. Okay, so we'll come back to why this is important as we go through the talk. Next slide. And another really important observation, this is at the present day. This is some modeling, this is some work done on modeling how much new crust is being formed versus how much is being recycled through various different mechanisms. So as it turns out, when you do this mass balance exercise, you're generating as much new crust in arcs and in hotspots and in other tectonic settings, mostly in these sorts of areas, in arcs. So you're generating around as much new crust as we're actually losing crust by recycling. Okay, so at the present day, we are not actually generating new crust, so it seems. Okay, so that's quite different, as we'll see when we go back in history. So yeah, these are things just to kind of remember as we go through the talk. So next slide. So the next part, so we've dealt with the continental, first of all, introduction to what the continental crust is. We've had a quick look at reworking of the continental crust in a plate tectonic regime. The next thing that's exciting to me and Simon in particular is the metamorphism of particularly bits of oceanic lithosphere. You know, when we form new oceanic crust, that often will be interacts with the seawater and forms low temperature hydrous metamorphism. And when that oceanic lithosphere gets subducted, it goes down to high pressures at relatively low temperatures, where we get this specific type of metamorphism in modern style subduction zones. Next slide. And we form these types of rocks, so green schists, epidote blue schists, and various types of eclogites at greater depths. And they are hydrous until they get to higher temperatures in the slab, where all the water is driven off into the mantle wedge, melts the mantle wedge, and we form arc volcanics. And that's where, of course, we can form this new crust. Okay, so there's an intimate link between crustal growth, potentially, and this type of metamorphism. Okay, yeah, next slide. And the other thing, the other bit of hallmark then is these paired metamorphic belts. So a Japanese geologist called Miyashiro first came up with this concept in the early 60s, where in the Sambagawa belt in Japan, he noted by mapping that there were two belts, a high pressure, low temperature belt of metamorphic rocks, which are towards the ocean, and then internal to that was a high temperature, low pressure belt of metamorphic rocks. And this is explained by having a subduction of a slab, so oceanwards towards a continent, taking down this cold lithosphere to high pressures. But in the hanging wall, because we have this melting and arc volcanism, we actually have a relatively high temperature but low pressure style of metamorphism. So another thing to look for in the rock record is whether we have evidence for these sort of paired metamorphic belts in the ancient past. Okay, so those are the sort of bits I'm going to focus on as we go through the evidence now that I'm going to present in the next slides. Okay. The last bit as well, just to remind us, I'm sure we're aware of the concept of supercontinents. So here's Pangaea, the last supercontinent, breaking up and spreading towards the present day. So again, in a plate tectonic regime with modern style plate tectonics, we would expect to see cycles of the breakup and formation of supercontinents in the ancient rock record. Okay, so that's the final bit of evidence we'll discuss. Next slide. Okay, so what we're going to do now then is look at some of, obviously the continental crust is a massive thing, so I'm going to focus the evidence on addressing the question, obviously. So this is a histogram showing the frequency of the ages of juvenile crust or granitoids. So that means rocks which were added to the crust by melting the mantle. So these are new additions representing crustal growth through the rock record. And as you can see, you have these strong peaks at around 2.7, 1.9 and 1.2 gigayears. Okay, so in this early compilation from Kent Condy, suggestion might be here that the continental crust didn't grow continuously, it grew in pulses. Okay, so we go to the next slide. That kind of begs the question, or it has done for a long time, of whether the growth of the continental crust is actually formed episodically by plumes. Plumes would be one way where we melt the mantle in kind of batches. So super plumes would be times of Earth history when there was a big plume forming lots of new crust. Okay, versus the other idea from the geochemistry and from plenty of other geological evidence that continental crust is actually being formed by subduction. Okay, so there's a dichotomy here, and this is something that's been argued about for some time. And we will go through and hopefully give you some ideas on current thinking about this particular conundrum. So next slide. The other thing in the continental crust is actually the types of igneous rocks that are being formed through time and what that might mean for the processes that have happened and how they've changed through time. So as it turns out, there is a secular evolution of the types of granitoids being formed. So in the Archean, we formed mostly tonalite, trondhjemite, granodiorite. So if you go to the Lewisian complex of northwest Scotland, these are the main rock types you'll find there. Okay. And now at the present day, and going back to the sort of end of the Archean, we have most of our igneous rocks formed in arcs are what we might call basalt, andesite, dacite, rhyolite, or calcalkaline type of magnetism. They're quite different chemically and petrologically to these TTG rocks. Okay, so there's a change in the type of magnetism happening, which might reflect the type of tectonics, it might reflect the heat of the Earth at the time, but clearly there's something process-wise that's happening. And in between those two types of rocks is a lovely bunch of rocks which are called sanukitoids, and these are different again in the sense that their chemistry is particular in having high amounts of barium and strontium and very light rare earth elements. And so models of why we might generate these different types of magnetism have come up with models like this, which show that the angle of subduction steepening through time, such that in the early parts of Earth history, the slab itself is mostly melting and is not being subducted steeply. And through time to the present day, where we now have deep subduction, and this thing here we call a mantle wedge, and we have dehydration of the slab and modern style arc volcanism. Now, in between those times, we had something which is a bit of both. So it seems to be having some input from subducted sediments, okay, but it's not exactly the same as this style of magnetism or this style of magnetism. And this style of magnetism started to occur in the rock record around 3 billion years ago, okay, over a billion or so years. And so the question then is whether this evolution represents a major change in tectonics, or it certainly represents a major change in process, but is that the onset of plate tectonics, of modern style plate tectonics? Okay, next slide. And as it turns out, on each different craton on Earth, we see this evolution from, in yellow here, so time is on this side now, going from older to younger, yellow being TTG style magnetism, and blue being these sanukitoids, and then pink and these clearer colors are hybrid granites or sort of S-type, biotite, 2 mica granites. As you can see, on each craton you have the same evolution, but the timing at which it reaches this kind of peak is different. So that suggests here, as we can see shown in a different orientation from older to younger, that we have TTG in blue to red in sanucitoid. We have a diachronous evolution. So each craton is evolving independently. Okay, so in other words, we might be kind of asking the wrong question if we're looking for a smoking gun for the start of modern style plate tectonics, if this is indeed tracking that evolution. Okay, so that's one important part of the discussion. The next slide. And so really, we are kind of just in this kind of question still, I think. I mean, really whether we have a kind of modern style of plate tectonics or something which in the Archean people think might have looked very cartoony, like this, vertical tectonics, where we have things dripping down into the mantle rather than being subducted with a steep dip like this. So really, you know, we're in this argument of when we had this style of tectonics versus this style of tectonics. Okay, now what I've just mentioned about this these models for forming these sanucitoids would tend to suggest that we might have this modern style of plate tectonics when they start to form, because we have this mantle wedge here, okay, rather than this type of style. So next slide, please. However, it's not quite that simple, unfortunately, because there are other ways that we can generate things that look like these kind of subduction zones, but are not long-lived and do not transfer material necessarily all the way down to the core mental boundary. So this is a paper from John Bedard a few years ago, where, again, cartoony shows that in this earlier kind of hotter style of tectonics, you might have bits of subcretion which open up these kind of pseudo-mantle wedges, and we can have some processes, such as local rollback, which would allow the mantle above it to look like this kind of hybridized, hydrated mantle wedge, which can then later be melted and form this kind of sanucitoid style of magnetism. So unfortunately, the chemistry itself does not solve the problem. Okay, it definitely shows that something is changing on a global scale, but by itself, you can't use that evidence alone to say this is when plate tectonics, modern style plate tectonics began. So we need something else. So the next slide, we are going to look now at what else we might be able to do with the continental crustal record by not looking at the rocks themselves, but by looking at robust minerals that grow within those types of rocks, within granitoids. So zircons are a mineral which is ubiquitous in evolved igneous rocks, in granitoids. And because they are so long-lived, when the granites are eroded, the zircons will end up in sediments and they will last there pretty much forever. Really difficult to destroy zircons. So that's why we have the oldest bits of Earth's crust are detrital zircons. Now, the reason why I'm showing you this graph is because this is a comparison between orogenic granitoids, which is essentially the same histogram I showed you a little while ago, compared to modern river sediments and ancient sediments. And they've taken zircons, detrital zircons, from modern and ancient sediments and compared those to the granitoid record. And as you can see, there's a really strong correlation in all of those peaks. So in other words, to cut the long story short, we can use the detrital zircon record to interrogate crust which is no longer there or difficult to sample. So we can use the fact that we have all of these sediments lying around and they always sample very, very ancient bits of crust because the sediments will just keep on reworking those zircons. So if we can find ways to use the zircon record to say more about these crust-forming events and perhaps other things, then we might have a better record to interrogate statistically, and that hasn't been hampered by perhaps rocks being reworked and eroded and so on. The next slide. So here is an image of a zircon. and this is a cathodoluminescence image. And we can see the interesting thing about zircons is that they're so long-lived that they can preserve bits of really old zircon and that have been overgrown in younger magmas, which then have overgrowth of younger zircon. And this can happen several times within one single grade. So we can see here this zircon has a core which is 3.4 billion years old, overgrown by a rim, an igneous rim at around 2.1 billion years. Okay, now that's the age itself is useful, but what we can also do is measure hafnium isotopes within these zircons in exactly the same place. And I don't want to kind of overkill you with isotopes here, but essentially, to cut a very long story short, this hafnium isotope signature is epsilon hafnium. This is the line which we inherited from chondrites, which formed the Earth. And as we started to melt the Earth to form the core, the mantle, and the crust, the isotopes went in different directions during those melting processes because the parent and daughter have different compatibilities. So that means we can use it as a tracer for when rocks were extracted from what we call a depleted mantle. So a very simple illustration of that. So this zircon here crystallized at 700 million years ago. It has a certain hafnium isotope signature, which we can trace back to this depleted mantle curve, and we can read down to a hafnium model age. That tells us that although the magma was generated at 700 million years, ultimately it came from material which was ultimately extracted from the mantle nearly 2 billion years ago. Okay, so the age of the zircon itself only tells you the last crystallization of that zircon. It doesn't tell you ultimately when it came from the mantle. And as I mentioned before, we need to know when the crust was actually growing if we want to use it in that way to interrogate the growth of the crust through time. And the next slide adds to the complication further, because we might be not only remelting igneous crust that was already there, we might also be adding, be introducing sediments, which are remelting as well, which skewed us the hafnium isotope signature even more, so that the mixture that we have doesn't represent a real crustal input age. So in other words, if we want to use these zircons well, we have to measure not only uranium lead age, hafnium isotopes, we also need to measure oxygen isotopes. So oxygen isotopes, delta 18 oxygen, we have a line here which is the mantle zircon value of around 5.3 per mil. Okay, so in other words, if we melt the mantle, we form an igneous rock from the mantle, the zircons will have an isotope ratio of around 5.3 per mil. If we add in sediments, then that's going to make those a lot heavier. So way over here, okay. And the only time when we go in the other direction is if we have high temperature hydrothermal alteration on the sea floor. So it actually turns out that this is a very sensitive tracer of the addition of sediments to our igneous rocks, and therefore it's a good screener for that extra addition that we're trying to screen out. I won't explain very much this diagram, but what it's tempting to show is that we can use the two isotope systems, hafnium and oxygen, to even model how much of our igneous rock contained mantle and how much was reworked sediment, so we can actually get a real number, quantification, on the amount of new crust that's formed that's represented by that zircon. Okay, so now I've got through that quite tricky bit, we can make a leap to actually what the data show us and why it might be interesting. So next slide. Sorry, one last complicated. This is from Eastern Australia. And what this diagram attempts to show here is the hafnium isotopes against the age, and they are color coded or shaded in terms of their oxygen isotopes. So the black colors are oxygen isotopes below 6.5 per mil, and the gray and white are above that. So the black colors represent what I would refer to as juvenile magma. So that came from dominantly from the mantle. The other ones are hybrid. They are mixtures of the two. Okay, so this whole kind of, we just took the data set without the colors and regressed them all back onto this depleted mantle curve, you get a mixture, a big hump of ages. But if you screen it for oxygen isotopes, you end up getting dominantly two peaks of ages. So what it's done is it allowed you, the isotope approach has allowed us to deconvolve all of that data and find out the dominant ages of mantle melting and new crustal addition to Eastern Australia. Okay, and next slide. So what we did some time ago was to try and take a more global approach to this from detrital zircons and see what that means through time by taking a large detrital zircon population. Basically here we have greys, which are oxygen isotope values which are not considered mantle-like, and all the green ones are mantle-like. And so the histogram here, which looks very much like that histogram I showed you before for granites, but now these are detrital zircons. The green ones represent these mantle-like oxygen values, and the grey ones are mixtures or hybrids. So what you can see here, hopefully, is that there's a more dominant peak of juvenile type magmas represented in the Archean than there is at later times. And if we model proportion of those and fit curves to them, we can see there's a very different curve, flat curve, in the Archean, and this parabolic curve relationship from the Archean onwards. Okay, and now we can, next slide, please. What we can actually do is we take this same kind of modeling. I can't go through all the modeling, but we can turn this into a diagram which represents the volume of continental crust added through time, so 0 to 4.5 billion years. And we can see here that there was a higher growth rate of the continental crust prior to 3 billion years, and there was an inflection, and afterwards there was a much slower growth rate of continental crust. So that's something that starts to look, having gone through all those leaps, the complicated isotopes, starts to look something tangible in terms of some process happening globally which might be related to our central question. The next slide. And the other thing, around the same time as we published this, there was another really neat paper which looked at a kimberlite from South Africa. And what they did was they got diamonds out of this kimberlite pipe, and they were able to date the diamonds by rhenium osmium isotope methods. And they were also able to find inclusions of pyroxenes inside the diamonds. It's very common to find pyroxene inclusions in diamonds. And the composition of those pyroxenes, they could distinguish whether they were peridotitic, i.e. mantle-like, so that means the diamond trapped material from the mantle, versus eclogitic, which means oceanic crust, which has gone down into the mantle, and the diamonds have grown around bits of old oceanic crust, essentially, or old eclogites. What they showed, which is really neat, is that around 3 billion years ago, there was a change from dominantly peridotitic clinopyroxene inclusions in the diamonds to dominantly eclogitic. Okay, so those two things, 3 billion years, seems to suggest something similar is happening. So next slide. And the other thing to mention about this crustal growth curve that I just defined is what else it means. So here are not only our crustal growth curve, but some others as well. They all agree more or less. So in this case, going left to right, just to confuse you. So 4.5 billion years to present day. So you can see this dominant early crustal growth and then slower. But this is the present day age distribution of juvenile crust. Okay, so obviously what that must mean is that this material has been destroyed because this is what we only see now, right? So the other thing it means is actually, although it's a change in the amount of new crust that was being produced, it's also a change in the amount of crust that was being reworked at that time. You can see there is a greater amount of crustal reworking, the difference between these two curves in the Archean, and that gets less and less through time. So, and that would really suggest, again, a change in tectonic environments, which explains that change in reworking. Got a change in the amount of crust being generated and a change in the amount of crust being reworked. Okay, next slide. Which leads to cartoon diagrams like this. So we put together those various records, crustal growth curve, diamond inclusions. Then this you can start to suggest, well, maybe we had some different style of tectonics before 3 billion years, with dominantly vertical style plate tectonics with plumes. And then after 3 billion years, we started to have something with subduction zones, which might be something like plate tectonics. Okay, so these are sort of consistent, but it's still really the question of whether this thing, which looks a bit like plate tectonics, really is the modern style of plate tectonics. And that's the point where I started to look at other records. So next slide. Oh, the other bit to mention here is that because we have this kind of this evolution in magmatism from TTGs towards these sanucitoids, and finally these kind of hybrid granites, it suggests that we have actually an evolution from the Archean to the later Neo-Archean, where we started to have cratonization, building thick cratons, which are then difficult to rework later in Earth history. So we can able to move those around as stable continental fragments, and when we have supercontinents, because they are strong and can be moved around and will not be completely destroyed. Okay, the next slide. So the other part of this record that we haven't really addressed yet is why we have these peaks in ages. So detrital zircons, which have these strong peaks, and I've mentioned, we have this dichotomy of whether it's subduction related, which you would expect to have a smooth peak of crustal growth, versus having plumes, which might form periodically. The other thing that is periodical in Earth history are supercontinents. Okay, so here in grey are the proposed tenures of different supercontinents. So you see Pangaea, Gondwana, not the true supercontinent, but mostly Rodinia, Nuna, and Superior/Clavia. So there seems to be some correlation, if you believe the data, with supercontinents and these detrital zircon age records. Okay, next slide. And just to go back through, if people are not so aware of the supercontinents in Earth history, the first supercontinent has been variably named as Kenor Land. Okay, and this is a true supercontinent when all of the bits of continent at that time were considered to be joined together. There has been another suggestion that it was actually two supercratons, which weren't actually contiguous, called Superior and Sclavia. And there's even people that's proposed that actually none of the above is true. So it's obviously a very difficult problem to try and solve. Okay, but this supercontinent or supercraton, most people accept formed around 2.7 billion years ago. Okay, so next slide. And then after that, we have, and just this slight historical perspective here, there are various proposed names which you might come across in the literature for the next supercontinent in the Paleoproterozoic. Nuna, Nina, Columbia have all been suggested, and they were based on different paleogeographic reconstructions going back to the 90s and younger. The details don't really matter. I just wanted to show you that there are various different configurations. So next slide. This is Columbia, and various different configurations have been suggested for that. And then next slide, the latest one that I'm aware of is this configuration called Nuna, which has good, reliable paleomagnetic poles, and does suggest that we had one single supercontinent around, which started to form around 2 billion years ago or so. Okay, now next slide is Rodinia, and again you can see many different iterations before people have converged on one solution for the for this supercontinent. Next slide. and this is from the latest one that I'm aware of, with Rodinia forming all continents together by around 1,000 million years ago, but then starting to break up by about 800 million years ago. Okay, so anyway, the main point here is there is good evidence, and you're aware of the evidence for Pangaea, of supercontinents being formed more than once in Earth history at around the same time as these age peaks of detrital zircons. So next slide. Bit more. Rodinia breaks up, and again, sorry, and we're aware that it came together as Pangaea, and it's broken up to the present day. So this is just to hammer home the point I was making. Next slide. Okay, so this diagram brings together various lines of evidence and proposes, again, the tenure of these particular different supercontinents based on various lines of evidence: detrital zircons, passive margin settings, detrital zircons in river sands rather than rocks, the age of eclogites, although these older ages now are not believable, and the ages of granites. And really the only point to make here is that if there is got to be some plausible link between the type of tectonics happening and the reason why we have pulses of these detrital zircons. Okay, so if we're not going to explain it by having superplumes, what other mechanism could there be for linking potential plate tectonics with this peaked record? Okay, next slide. And if we consider where new crust is being formed at the present day, or in recent times, we can start to conceptualize how we might think about this. So if you look at the Cordilleran accretionary origin, the western side of the Americas, there's lots and lots of magmatism. I'm sure you're aware, lots of volcanoes, lots of plutons at depth, and lots of potentially new crust. Okay, as it turns out, and based on, if you remember that diagram I showed you very early on in the talk, there is actually no new crust being formed net in these settings. So it's being eroded and it's being reworked back into the mantle down subduction zones as quick as it's being formed by magnetism. So in other words, these types of settings, exactly where you might think that new continental crust is being formed, is actually a really bad place to form long-lived new continental crust. However, if we think about the Himalayas forming, so India drifted northwards and finally started to collide 50 million years or so ago with Asia, and between them was originally a subduction zone, and there were arc magmatism. And actually, as we started to close that subduction zone, close the ocean, that material is now being rather nicely preserved in the origin, in the mountain belt. So we have thick crust in Tibet. So in other words, although there's going to be less and less magmatism as the ocean closes, the preservation potential becomes much higher. Okay, so there's a tectonic setting relationship between the amount of magma being produced and the amount likely to be preserved. Okay, so next slide. And this is a very cartoony diagram of that relationship. So here's a supercontinent cycle. So from subduction, when all the continents are all spread far apart, you're obviously going to have lots of subduction zones around them as they start to move together inexorably towards having the next supercontinent. So you're going to produce lots of magma globally as a result. So the volume is going to be high. However, the preservation potential in red is going to be low. I'm not going to get into this difference between retreating and advancing subduction zones. The preservation potential is going to vary, but it's generally going to be very low. Okay. Now, when you come into a supercontinent, your magma volume will start to drop because you have less of these subduction zones and eventually none. But the preservation potential will increase for those reasons I just talked about when the Himalayas was forming. Okay. And then we start to break up the supercontinent. We have more magmatism, but and we go back to having very low preservation potential in these extensional settings. Okay, so next slide. And what we suggest is that there's this kind of sweet spot during supercontinent formation, where the amount of magma being formed is being preferentially preserved. So in other words, because these are where we're forming most of our granites that are eventually being eroded into our sediments, we end up with a preservation bias which gives us the age of these peaks. So in other words, there should be a strong link between these ages and the presence of some kind of plate tectonics. Okay? So that still leaves the question of whether all of this from 2.7 represents modern style plate tectonics or a change in some ancient style to a more modern to modern style. And the big question still is when that actually happened. Okay, next slide. So now we turn finally to the metamorphic record. So just to define what these different colors mean, basically. So the important ones based on pressure and temperature are what we call basically high pressure, low temperature. What we call here low DT over DP. So the blue colors are the sorts of rocks we find in modern style subduction zones. Okay. The green colors are hotter, and this is in these letters here means B for blue schist, E for eclogites, E for UHP, and HPG is high pressure granulite, G is granulite, and UHT is ultra high temperature. So if these are all our sort of subduction zone style rocks, these ones over here are hotter and not generally found in modern style subduction zones, but that might be that in the past when Earth was hotter, when the mantle was hotter, it was these types of rocks which were being formed in things which kind of looked like subduction zones but weren't exactly the same, if you see what I mean. Okay, so just follow the colors really. Blue is our subduction zone style, red are much hotter rocks, and green are these intermediate, high pressure but low high temperature as well. Next slide. Now, if we take the rock record, look at all metamorphic rocks, as Mike Brown and Tim Johnson have done exhaustively, and plot those up on temperature versus time, okay, we can see that we have a lot of these subduction style rocks from around 800 million years or so. Okay, now for some, this meant that they considered that only modern style plate tectonics only started in the Neoproterozoic. Right, now I've always thought that could be a preservation issue because these rocks are very difficult to preserve. They become retrogressed, they become weathered, and so it might be a preservation issue. And that has come to pass because in the last couple of years people have started to find evidence for these sorts of rocks, not quite as cold, but these sorts of high pressure, low temperature rocks popping up at around 2 billion years or so. Okay, so already we kind of pushed this rock record of potential subduction back to about 2 billion years. But the rock record is difficult. So what would be nice is if we had a mineral like zircon, which we could use to try and look in sediments, which are going to then sample lots and lots of metamorphic rocks, which either we can't find or can't get to, covered by glaciers or have been eroded, etc. Okay, so next slide. And the mineral rutile, I will hope to persuade you, is kind of the zircon of metamorphic rocks. So rutile is titanium dioxide, along with a bunch of other high field strength elements, and it's common in high pressure metamorphic rocks. So here's a big glaucophane, there's a blue schist, and a nice big rutile. And I could show you any eclogite, and they always have rutile in them as well. We are able to date rutile in the same way as we can with zircon. We can measure the zirconium concentration in rutile as a thermometer to work out the temperature of metamorphism. And we are also able to analyze chromium and niobium concentrations. They can even tell us whether the protolith, the starting rock type which became metamorphosed, was a sediment or was oceanic type lithosphere with metabasalt. There's quite a lot of stuff we can do with rutile. The next slide. And the interesting thing straight away is that if we look at the stability of rutile, it's a phase diagram, so pressure versus temperature, and rutile is the high pressure titanium rich phase in mafic rocks. So at lower pressure would either have titanite or ilmenite. So already if you find rutile and you know it's metamorphic, and particularly if you know it's from a mafic protolith, then you know it must be a relatively high pressure metamorphic rock that it was eroded from, if you're looking at sediments. And here is a discrimination diagram for chromium and niobium, telling us whether the rutile came from a metamafic source or from a metapelite. Okay, and then finally, this is a calibration for our zirconium thermometer in rutile. So these are the tools I'm going to use along with uranium lead dating to look at the rutile record, the detrital rutile record. Next slide. And yeah, sorry, fine. This is also another diagram which kind of shows the concentration of zirconium in rutile against metamorphic facies. So I've already sort of shown you that to have rutile at all, if you know it's from a mafic source and it's metamorphic, then you must be dealing with relatively high pressures. And if you know the zirconium concentration, we could tell if it's very low zirconium that it would be coming from a blue schist facies type of rock. And at high temperatures, it would be coming from eclogites, and really high temperatures, it would be coming from a granulite. So in other words, if you remember those different colors that I showed you, then our rutiles could be matched on to those different colors. Next slide. And that's exactly what we've done. So the sample is still relatively low at the moment because this is, you know, relatively new technique. But if we plot detrital rutiles through time, the yellow colors are rocks from metafelsic or metapelitic, metasediments basically, protoliths, and the blue are from metabazites. And then we've got temperature against age, and you can see here that we have peaks in ages around sort of Gondwana times, Rodinia times, and Nuna times, and then back to Kenorland or Superior Sclavi, if you want to call it that. So there are peaks in the ages, just like there are with the zircons. There are also changes in the range of temperatures through time as well. So in the Archean, we have a much restricted range of temperatures. And then when we get to this 2 billion years, when Nuna is starting to form, we start to form a much bigger range, which we infer to be two things. These lower temperatures are related to these high pressure, low temperature metamorphic rocks like blue schists and eclogites. And the range represents paired metamorphism. So those are the two hallmarks I was talking about in terms of the metamorphic record for when modern style plate tectonics, we can find it in the rock record. So what you can see here is that there's no evidence in the Archean for this type of metamorphism, but there is once we get to Nuna. Okay, so next slide. And the other thing we can pull from this data as well is because the rutile ages now, the brown ones, against the grey, which are detrital zircons, because these age peaks, there is some sampling bias in this because it's not a big sample set yet. But from what we can tell so far, the age peaks agree quite nicely with the zircons, which tends to suggest that we might have the same preservation bias happening in the detrital rutile record as in the detrital zircon record, which then tends to argue in favor of this preservation bias for the detrital zircon record. So it's being preserved preferentially by having this kind of plate tectonic process. Okay, but there does seem to be a change, a big change in the style of metamorphism, the style of tectonics from the end of the Archean to the Paleoproterozoic. Okay, next slide. So now we can kind of get towards the end and we can try to put things together. So in grey, again, it's a detrital zircon histogram record of age. And now we've got reds and blacks in this particular case. Reds are the very high temperature metamorphic rocks. Blacks this time are the intermediate, and blues are the low temperature, high pressure ones. So you can see that we have kind of starting to get this nice record of having agreement in the age peaks and having these sort of paired extended range of metamorphic conditions along with high pressure, low temperature rocks from the Paleoproterozoic onwards, but not in the Archean. And when you plot that against, this is known as the Great Thermal Divergence. This is potential mantle temperature through time. So the mantle started to cool relatively rapidly in the Paleoproterozoic. So that means likely that it was able to support a modern style of plate tectonics because the mantle wasn't so hot, essentially. And we can also see these other records where continental crust, generation of continental crust changed and the amount of reworking changed. So there was a change in the style of tectonics, but that might not be actually related to modern style plate tectonics. Okay, and finally we can see this evolution of TTGs through to Sanucitoids through time, showing a very diachronous evolution. Okay, in different cratons. So next slide. And so a slightly different version of the same thing here, but really this is cartoons to show what we think might be happening. And this is where the big debate starts. So we think before about 3 billion years or so, the style of tectonics was really what we might call pre-plate tectonics. You might have had things which kind of looked like pseudo subduction zones, but they can't have been long-lived, they can't have been ongoing, they can't have been perennial, and most of the tectonics was vertical. And then we have a transition phase from around 2.7 to 2.1 billion years, gap between here and here really, where we had something which looked like subduction, you might call it subduction, but it didn't have all the hallmarks of modern style plate tectonics and was likely not a continuous interlocking perennial rigid bits of lithosphere moving against each other in the way that we define plate tectonics today. Then after about 2.1 billion years, we start to have something which we might be more confident in calling modern style plate tectonics. Okay, so next slide. So I just very quickly, I just want to show you what we're going to do next really. And this is looking at how we can actually try to look at the interaction between the surface, so the atmosphere, and the mantle through time. Because obviously, if we have an evolving atmosphere, then we're starting to have subduction and plate tectonics. There ought to be a link between the two. Okay, and it turns out that this is a problem that people have been trying to address for a very long time using lots of different methods. And the real interesting thing is the evolution of atmospheric oxygen. So 4 billion years to the present day, we know the great oxidation event occurred around 2.4 billion years ago or so. And a big increase in oxygen in the atmosphere, started to have proliferation of life, banded iron formation, terrestrial red beds, etc. And that happened in stages, so there was also a Neoproterozoic oxygenation event as well. So just in this study here, we've used a new method, again in zircons, you get the message with what we do mostly, to try and trace this event. So the next slide just shows you a very quick cartoon of the results of that paper that we've just had published this year. And what we did, we looked at these zircons from rocks which are around 2.35 billion years ago, from TTGs in Brazil. So they are either before or around the same time as the Great Oxygenation event. So these are rocks which came from the mantle 2.35 billion years ago, and rocks which are around 2.13 billion years ago, which are these Sanucitoids. So in other words, these are rocks which came from the mantle but also had the inclusion of sediments in their petrogenesis. And they were formed after the Great Oxygenation event. And what we found when we looked at inclusions of a mineral called apatite inside these zircons is that we only have reduced sulfur species in the apatites in these older TTG samples, but we have only oxidized sulfur in the ones which are after the Great Oxygenation event. So as these both come from the same mantle, which has just evolved through time, we've added sediments and we think what we've done is actually taken the oxidized atmosphere in the form of sediments, taken it down into the mantle, and sampled it in igneous rocks after the great oxygenation event. So, so this is hopefully a new tool. We can start to look at the evolution of the interaction of the mantle and the atmosphere through time as well. So next slide. This is the end. Yeah. So in conclusion, so the continental crust started forming over 4 billion years ago, but cratons didn't stabilize until around 3 billion years ago. So we had some different type of tectonics, thinner crust before that time. And then we started to have some kind of plate tectonics because we have supercontinents or supercratons forming by around 2.7 billion years. But as far as we can make out, actually modern style of plate tectonics with high pressure, low temperature metamorphism and paired metamorphism didn't start until around 2 billion years ago. So in other words, there is and then subsequent to that, we know we have a very good record of these rocks from 800 million years ago or so to the present day. So my current thinking and my colleagues is that this is actually a diachronous onset of modern style plate tectonics, taking from around 3 billion years to 2 billion years to finally assert itself. And also the last bit is we've seen subduction does seem to be an efficient way of oxidizing the mantle, and we can trace this through time and hopefully add more to this evolution. Thank you very much for listening.